And also, here, this graph is to show you the difference between explained and unexplained heterogeneity. If we just, blindly use Poisson distribution without introducing, observed heterogeneity into the model to create this Poisson regression model, what's going to happen? Well, to kind of give you some rough idea what's going to happen, that is what? Poor prediction. So in this graph, right, on the left, let's say, we have two conditional distributions. So in this case, we have what is called explained heterogeneity because we know the heterogeneity, right? Let's say in this case is gender, right? And for women, we have what? Solid dot line. So this line here, okay? In this case, we know it's mu is equal to 1.5. Or that is the mu for women. And again, what we're going to do, we're going to plug in this formula. Probability of y given mu is, and actually in this case, we have additional variable that is x, that is gender, right? We know this is gender, all right? So this is gender. And in this case, it is equal to what? E raised to the power of negative mu for what? For gender. Okay, so this is for women. Then is mu for women raised to the power of y, then divided by y factorial. And we calculate, right? Y here is 0, y here is 1 and 2, and etc. etc. And then we do the same for men. In this case, men are on this, square and dashed line here. Okay, so this line, right? And its mean is 4.5. And here we can see, their difference in this case, right? For women, for lower counts, women have high probability, right? For high counts, men have high probability because, this just in lines with, one of the property as the mean or the expected count increases in this case, right? For men's, expected count is 4.5, and for women is 1.5. The distribution shifts to the right because the center goes to the right, right? And here's, the difference I want to point out. So for panel A is conditional distribution. Then people say, well, what is panel B? Panel B is marginal distribution. What we're going to do is we're going to mix these two distributions. There's two distributions. Okay, and then just lump them together, assuming we don't know anything about individual respondents' gender information. What's going to happen? Well, when we combine it, okay, the mu is equal to what? It's going to be equal to 3, right? Assuming equal size. So if we're going to plot the Poisson distribution, a theoretical distribution with mu equal to 3, okay, what we're going to see, the Poisson distribution, okay, it's going to look like exactly the solid dot line, okay? That is a theoretical probability distribution if mu is equal to 3, okay? How about the dashed line? People might want to ask, The dashed line here is a simple mixing of the two distributions here in the in panel A, males and females. Then what we're going to do is to calculate the observed frequency, then turn it into relative frequency. So these, empty square and connected with a dashed line here are observed relative frequency. Okay? So the solid dot line and the empty square dash line, they don't match exactly. They don't match exactly. Okay? And this shows the problem of unobserved heterogeneity. So the solid dot line represents the theory, a Poisson distribution with a mean of 3. Okay? And what we observe in real data is the dotted line, the dashed line, okay? So there's a discrepancy. And for the observed data, here we can see for the dashed line, we have high probability for lower counts, especially 0 and 1. And for other counts, actually, the theoretical distribution have high probabilities, right? Like this one, and this one. And this graph, panel A and panel B, shows the utility of explaining observed heterogeneity. And basically, in this case, is what? Known individual characteristics, okay? So what the Poisson regression model does is to add what's called observed heterogeneity to the model. When we say observed, it means, well, information we have in our sample. Okay? So how to do it? Well, the challenge here is to what? Is to figure out mu. Once we figure out mu, of course, we can figure out the probability distribution, right? So what Poisson regression model does is that it argues that the mu here, okay, is different across individuals with different observed heterogeneity or different characteristics, okay, for different variables, right? So how to model that? And since the count has to be, well, a positive number, it is considered to be expected rate or count given known heterogeneity or characteristics, a natural candidate for it would be exponential function. Okay, so everything plugging into this exponential function going to turn out to be positive. Okay, so we're going to have this structural model within the parentheses, right? Everything. Let's say x1, x2, and all kinds of known characteristics, right? We can collect from a sample and plug in here. In our last slide, it is gender, but it could be income, could be education. So anything we view as important in predicting this individual, right? Individual expected rate, okay? So what it does is to take exponential of x beta, forces the expected count mu to be positive,